Okay, think about this. Pretty much every living thing moves, right? But have you ever really stopped to think about the engineering behind it all? I mean, from just a simple wave of your hand to a bird soaring through the sky, movement is this absolute masterclass in biology. So today, that's what we're going to do. We're going to break down the mechanics of how we and a lot of other creatures get around. So let's go back to that simple wave hello. It feels like nothing, right? Totally effortless. But under the surface, it's actually this complex symphony of bones and joints and muscles all working together in perfect harmony. And to really get how it all works, we're going to start with the machine you know best, your own body. Then we'll branch out and see how other creatures have tackled the exact same problem of just getting around. All right, first things first, let's look at the foundation. I mean, right under your skin, there is this incredible framework. It gives you your shape, it protects all your vital organs, and it acts as the anchor for literally every single move you make. You know what I'm talking about? Your skeleton. So your skeleton has three really big jobs, and trust me, it is not just some passive scaffold just hanging out in there. Its first job, giving you your form, your shape. It also acts like a bodyguard for your most important organs. Think about how your skull protects your brain. And this is the really key part for us today. It provides that rigid structure that your muscles need to pull against to create any kind of motion. But not every part of your skeleton is super hard, rigid bone. Go on, try it. Wiggle the tip of your nose. Or your ear. See that? That's cartilage. It's the softer, more flexible part of the whole system, and it provides structure in all the places where you need just a little bit of give. Okay, so if the skeleton is the framework, the joints, well, the joints are the absolute engineering marvels that turn that static frame into a dynamic, moving machine. Seriously, this is where all the magic happens. And the definition is so simple. A joint is just the spot where two or more bones meet up. That's it. But without them, we'd basically be stiff as statues. Every single bend, every twist, every turn you can possibly make, it all happens right at these crucial intersections. But of course, not all joints are the same. They're not all created equal. So first up, we've got the ball and socket joint. And the best way to think about this is like a joystick. You have the rounded end of one bone fitting perfectly into a cup-like space in another. And that's what gives you that awesome 360-degree range of motion you have in your shoulders and your hips. Okay, next up is the pivot joint. And this is actually what's happening right now as you maybe nod your head or shake it. You've got a cylindrical bone that rotates inside a little ring, and that gives you that very specific rotational movement. It's this really elegant piece of engineering that lets you do something as simple as looking both ways before you cross the street. Now this one's probably the easiest one to picture, the hinge joint. It works exactly like the hinge on a door. It just allows for that simple open and shut back and forth motion. You've got these all over the place, in your knees, your elbows, and even in all the tiny little joints in your fingers. And then, just to round things out, there's one really important exception we have to talk about: fixed joints. Now, these are places, like the plates that make up your skull, where the bones have actually fused together. So their job isn't about movement at all. It's about providing rock-solid strength and protection. That makes them totally different from all the other joints we've just looked at. So, let's do a quick recap. We've got the ball and socket in your shoulder for that all-around movement, the pivot in your neck, letting you rotate your head, the simple back-and-forth hinge in your knee, and, of course, the immovable fixed joints in your skull. That's it. That's your body's complete toolkit for getting around. Okay, so having an internal skeleton is obviously one way to build a body, a pretty successful one. But what about the vast majority of creatures on this planet that don't have one? How does life get around when there are no bones at all? Let's dive in. All right, let's take the humble earthworm. Its body is basically made of rings, and its movement is this fascinating cycle of muscle contractions. So what it does is it extends its front half, then it uses these tiny little bristles on its underside to anchor itself, to grip the ground. And then it contracts and pulls the back half forward. It's kind of like this inch-by-inch muscular wave. And then you've got the snail, which has an equally clever solution, even if it's a little bit slower. It moves on one single giant muscular foot. And if you ever watch one close up, you can actually see the waves of muscle contraction rippling along its body, pushing it forward. And that famous slime trail, it's not just goo. It's actually a specially engineered lubricant that cuts down on friction, which is super important when you have to drag a heavy shell everywhere you go. Okay, let's switch gears to a completely different strategy. Instead of having your skeleton on the inside, what if you wore it on the outside?
like a built-in suit of armor. Well, welcome to the world of the exoskeleton.
So right here, you can see the two fundamental blueprints for building a body. On one hand, you've got us, with an internal skeleton and muscles attached on the outside. But an insect, like a cockroach, it flips that idea completely on its head. It's got a hard outer shell, and all of its muscles attached to the inside of that shell. It is a totally different approach to solving the exact same problems: support, protection, and of course, movement. And inside that suit of armor, the cockroach is a super efficient machine. It's got its 3 pairs of legs for walking and usually 2 pairs of wings for flying. But here's what's really wild. It has completely separate sets of powerful muscles tucked inside its torso to power these 2 different kinds of movement. One set just for the legs and a totally different set just for the wings. It's incredible. All right, let's head back to creatures with internal skeletons like us, the vertebrates. But this time, let's look at the ones that have absolutely perfected moving through totally different environments. I'm talking about the masters of the air and the sea. When you look at a bird, literally every single part of its body is optimized for flight. To keep their weight down, their bones are actually hollow. Their forelimbs evolved over millions of years to become wings. And the real power for flight, that comes from these huge breast muscles anchored to a super strong breastbone. And that's what creates that powerful flapping motion. It is a true masterpiece of lightweight engineering. The way a fish moves, man, it's just pure fluid dynamics. Its streamlined body makes this perfect S shape, and by rapidly snapping that curve back in the opposite direction, it creates this powerful jerk that literally pushes against the water, shooting it forward. It's just this elegant, powerful dance between muscle and water. All right, for our last example, let's look at one of the most unique ways of getting around in the entire animal kingdom. We're talking about a creature that has a backbone, but 0 legs. Let's get into the art of the slither. So, how in the world does a snake move so fast? Well, it's not magic, it's pure physics. The snake bends its long, muscular body into a whole series of loops. Then, each one of those loops pushes backward against the ground. Each push is small, but when you add up all those small pushes together, you get this incredibly powerful and continuous forward motion. It's just unbelievably efficient. So when you think about it, whether it's the internal toolkit of bones and joints we have, or the external armor of an insect, or the amazing legless propulsion of a snake, it's just so clear that nature has found countless ingenious ways to solve the problem of movement. Life is like the ultimate engineer, right? It's always experimenting, always optimizing, and that really makes you wonder, what incredible new solution is it working on right now?